The constituent particles. The particles can be atoms, molecules or ions. They have fixed positions. Solids have definite mass, volume and shape. The intermolecular forces are short. Intermolecular forces are very much strong that the constituent particles are arranged very much closely. The constituent particles oscillate about their mean position. They are incompressible because the space present between the atoms is much lesser. As a result of this, the solids are rigid in their structure. These solids can be classified into two types. One of the type is crystalline solid and the second type is amorphous solid. Crystalline solids consist of a large number of small crystals and each of them have a definite characteristic geometrical shape. And the constituent particles are arranged in an ordered manner. There is a regular pattern of arrangement of particles and this arrangements repeat itself periodically over the entire crystal structure. So, I can tell that the crystals have a long range of order. At every point, if you check, the arrangement of particles will be observed as the same. For example, we can consider sodium chloride, quartz, iron, silver, etc. All these are the examples for crystalline solids. The word amorphous is derived from the Greek word which has meaning no form. So from this name, we tells that amorphous solids consist of particles of irregular shape. The arrangement of constituent particles. The particles can be atoms, molecules or ion. They has only short range order. In such an arrangement, a regular periodical arrangement of atom is observed only for short distances. Although amorphous solids do not possess long-range regularity, but in some cases, at a certain given region, there follows a ordered arrangement of atoms. So this particular part of the amorphous crystal, it acts as crystalline solids and that we term it as crystallites. The good examples for amorphous solids are glass, rubber and plastics. Here you can see the structure of crystalline quartz and quartz glass, which is the amorphous form of the quartz. The two structures are almost identical. But in the case of amorphous quartz glass, you can see that there is no long range order that is exhibited by it. Now it is clear for us that it is because of these differences in the arrangement of constituent particles, we have different properties for different types of solids. So what are the differences do we observe in the properties of these different solids? Crystalline solids have a sharp melting point and they are called as true solids. Whereas the amorphous solids, they melt over a range of temperature and can be molded into the different shapes that is required for us. And they have a tendency to flow. Because of all these properties of amorphous solids, they are known as pseudo-solids or they are also called as supercooled liquids. It is observed that glass panes fixed to the windows or doors of old buildings are found to be slightly thicker at the bottom than at its top. Can you think of why? This is because the glass flows down slowly and makes the bottom portion slightly thicker. Crystalline solids are anisotropic in nature. What is anisotropy? It means that the different physical properties, when you measure along the different directions in a same crystal, you will get the different values. For example, if you measure the physical properties such as the refractive index, you will find the different value in different direction for a crystalline solid. From this image, you can see that the arrangement of particles is different along the direction AB and it is different along the direction CD. The value of same physical property is found to be different along the direction AB and along the direction CD. Whereas the amorphous solids are isotropic in nature. It is because the arrangement of constituent atoms is irregular along the different directions. When the arrangement of particles is different along the different directions, in whatever direction you measure the physical properties, of course you are going to get the same value, and therefore the amorphous solids are isotropic in nature. Now let us summarize these differences of crystalline and amorphous solids in a table. Crystalline solids have definite characteristic geometrical shape. It is because the atoms are present in their regular arranged positions. On the other hand, amorphous solids have irregular shapes. Crystalline solids melt at a sharp and characteristic temperature, whereas the amorphous solids, they gradually soften over a range of temperatures. When crystalline solids are cut with a sharp-edged tool, they split into two pieces and the newly generated surfaces are plain and smooth. But when we cut the amorphous solid with a sharp-edged tool, the two pieces which are obtained after cutting are having sharp edges. For example, you can consider a glass. Glass is an example for amorphous solid. We often see that when glass is cut into pieces, they are cut into sharp edges and we get our hands or body parts hurt because of these sharp edges formed after cutting. The crystalline solids have definite and characteristic heat of fusion, whereas the amorphous solids, they do not have a definite heat of fusion. Crystalline solids are anisotropic in nature. Anisotropy is the different properties, physical properties measured along different directions, you will get the different values. Whereas the amorphous solids are isotropic in nature. Try to recall what is isotropy. It is the different physical properties when you measure along the different directions, you will be getting the same value. Crystalline solids are known as true solids, whereas the amorphous solids are known as pseudo-solids or supercooled liquids. Coming to the arrangement of constituent particles in crystalline solids as well as amorphous solids. Crystalline solids have a long range order, whereas these amorphous solids have only short range order. Most of the solid substances present around us are crystalline in nature. For example, the metallic elements like iron, copper, silver, and the non-metallic elements like sulfur, phosphorus, iodine, and the compounds like sodium chloride, zinc sulfate, naphthalene, etc. are found in crystalline state. These crystalline solids can be classified into 4 categories, and these classifications is based on the nature of intermolecular forces between the atoms present in the crystals. So the 4 classifications are molecular solids, ionic solids, metallic solids, and covalent solids. The constituent particles of molecular solids are the molecules. These molecular solids can be classified as non-polar molecular solids, polar molecular solids, and hydrogen bonded molecular solids. Non-polar molecular solids are formed from atoms like argon and helium, or the molecules formed by the non-polar covalent bonds. For example, hydrogen, chlorine, or iodine molecule. The atoms or molecules are held by weak dispersion forces. They are also known as London forces. And these solids are soft and non-conductors of electricity. They have low melting points and are usually present in liquid or gaseous states at room temperature and pressure. The polar molecular solids are formed by polar covalent bonds, and the molecules are held together by relatively stronger force of attraction, that is the dipole-dipole interaction. These solids are also soft and they are non-conductors of electricity. Their melting points are higher than those of non-polar molecular solids, and most of these solids are present in their gaseous or liquid state under room temperature and pressure. The examples are solid sulfur dioxide and solid ammonia. The molecules of hydrogen bonded molecular solids contains polar covalent bonds between hydrogen and fluorine, oxygen or nitrogen atoms. The strong hydrogen bonding binds the molecules of such solids. For example, ice. The hydrogen bond between oxygen of one water molecule and the hydrogen of other water molecule binds them together. They are non-conductors of electricity. Generally, they are volatile liquids or soft solids under room temperature and pressure. As the name indicates, the constituent particles in the ionic solids are ions. The solid is composed of three-dimensional arrangement of cations and anions which are bound by strong Coulombic forces. The Coulombic forces are nothing but they are also known as the electrostatic forces. These solids are hard and brittle in nature. They have high melting and boiling points. They are electrical insulators in the solid state. It is because in the solid state the ions are not free to move around. But the ionic solids in their molten states or when they are dissolved in water, they conduct electricity. This is because in the molten state or when dissolved in water, the ions of the ionic solids become free and they move freely, so they conduct electricity. Metallic solids have a collection of positive ions surrounded by and held together by a sea of free electrons. These electrons are mobile, means which can move freely and are evenly spread out throughout the crystal. Each metal atom contributes one or more electrons towards the sea of mobile electrons. The metallic solids exhibit high electrical conductivity and thermal conductivity. This is because of the presence of free and mobile electrons. The examples for metallic solids are chromium, iron, gold, silver, etc. When we apply an electric field, these free electrons flow through the network of positive ions. When heat is supplied to one portion of the metal, the thermal energy is spread uniformly throughout the metal. This is mainly because of the presence of free electrons which can move around. Another important property of metal is its luster and color in some cases. This is also because of the presence of free electrons. Also, they are malleable and they are ductile. Malleability means that we can convert them into sheets, whereas ductility refers to the property which can make thin wires from the metal. A wide range of crystalline solids of nonmetals are obtained by the formation of covalent bonds between the adjacent atoms throughout the crystal. They are also called as giant molecules. As the covalent bonds are strong and directional in nature, these atoms are held very strongly at their positions. These solids are very hard and brittle. They have extremely high melting points and they decompose before melting. They are insulators and they do not conduct electricity. A good examples for these type of solids are diamond and silicon carbide. But graphite is an exception as it is soft and a good conductor of electricity. Just now we have studied that covalent solids are hard and brittle. But what makes this graphite as soft and a good conductor of electricity? Yes, it is its structure. The carbon atoms of graphite are arranged in different layers. So this structure you can visualize from the figure that is shown here. So these carbon atoms which are present in the graphite are arranged in different layers, and the carbon atoms are covalently bonded to 3 of its neighboring carbon atom in the same layer. The 4th valence electron of each atom that is present between the different layers, and they are free to move about. These free electrons make graphite a good conductor of electricity. The different layers can slide over the other, and this makes graphite a soft solid and a good solid lubricant.